Welcome on.
Thank you.
Hello.
Thanks for joining us today.
Yeah, glad to be here.
And you're in Ireland, is that right?
Northern Ireland, yeah.
Yeah.
That's a completely separate Ireland.
I was looking at that last night, and it's like its own, like the location you're at. Maybe I'm wrong, and maybe I'm looking
it's
too far. But
20 minutes from
Belfast.
Belfast.
It sounded pretty interesting.
Oh yeah,
Okay.
It is.
I thought you were American. Don't know why.
I thought he was too, actually. To be perfectly honest.
No, never been.
Never been to America?
Never been to America?
No, I've never been American.
Never been American.
Oh,
Okay,
yeah.
fair
That's
enough.
probably a good idea, actually.
Oh, no, I love
They're
America.
crazy. I know.
I love-
Those guys are crazy.
I love America.
Yeah,
I have ambitions to move there, so there you go.
Really? Okay.
Yeah. Anyway,
You know,
Don't let me stop you.
There's a joke in there, something about try to escape the Northern Ireland and the IRA, and then move to a place where Compton.
Detroit.
I don't know what the joke was there. I just don't know what it was going to turn into. But anyway,
yeah.
I took a shot at it.
We
nice
can
try.
work on it. We can work on it. It's
We'll put it
like
together.
1950. It's like 1950 here, so it would be a bit of time travel. Really.
Yeah, definitely.
Welcome to the November 25th edition of The Electric View. I'm Neil Thompson. Today we have Jim, Heather, Buddy, Robert, Eugene, and David with our special guest, Neil Kramer. We will be discussing advances and studies in the field of bio-nanotechnology and the electric nature of atoms, and speak on the new Mars lander and the odd surface features of other planets. Please like and subscribe.
Let's get because we have the guests. Let's get to the other Neil, and I understand like your background. It's chemistry and materials.
Yeah. I did my degree and PhD, and then research in materials chemistry for a while. I worked in what's called bio-nanotechnology. So earlier in my career, I had been a medical microbiologist in the health service. And then I did a few other things, ended up doing a degree later in life, and then a PhD in chemistry. And so that made me a good candidate to go and work in an applied microbiology lab. And it so happened that these people had been working on bioremediation, which would be familiar to Australians in particular, I think, where there's a mining industry, using bacteria to clean up mine waste and remediate the metals and whatever.
Right.
Anyway, so they stumbled across. They were doing that for a while. They stumbled across this thing of being able to recover precious metals. When you recycle electronic scrap, and one of the things they do is put it in aqua regia, which is like hydrochloric and nitric acid, and that leaches out the metals. And what you can do is you can actually put dead bacteria in, because they have sites on their surface. They have sites which are capable of reduction. Anyway, they would form nanoparticles on their surface. And so they were using these dead bacteria to recover metals from these solutions. And they got on to, they were recovering technetium for a start. And then I think they said, well, wait a minute, technetium, we've done that so we can recover palladium. And they recovered palladium. And that was about the time I came into the group. And what I was doing was I was taking these dead bacteria with the palladium nanoparticles on their surface and using them as a catalyst. In trial reactions, and they were very, very good because they were tiny nanoparticles, great surface area.
I have a question. Excuse me, Can I interrupt you?
Is
that are they like reducing the? As I understand, they're kind of. I don't know the proper word. I'm sorry.
It is reduction. Yeah, it is reduction.
Reducing. Yeah. So they're reducing the metals from the oxides. Is that correct?
Well, from solution. So They are sulfate reducing bacteria. I used the sort of thing you'd find in estuary mud. There's a species called Desulfovibrio desulfuricans, which reduced sulfate to sulfide to survive. That was its energy source.
Okay, so my question was basically, are they doing that, and this is sort of a hypothesis, are they doing that because of the electric potential on their cells? I mean, the bacteria?
Yes.
Yes. Okay.
Exactly. It's basically exploiting that ability of the bacteria. So what the bacteria would do, as I went on, because I looked more and more into this, it seemed that the bacteria would nucleate the particle and then they'd probably die because of the conditions. But the fact that they'd formed the nanoparticle nucleus meant that it could then grow autocatalytically, because what you'd do is you'd put these bacteria into the solution, leave them for a while to nucleate, and then you bubble hydrogen through. So the hydrogen would, even if you didn't have the bacteria there, the hydrogen would eventually reduce the metal out of solution. But the fact that you'd formed these nuclei on the bacterial surfaces meant that the nanoparticle growth took place there preferentially. So you basically seed the nanoparticles on the bacteria, and that kept them small as well. There were other advantages because it took place between membranes that limited the size. It was, fortunate, very fortunate that took place. Anyway, so I did some work with these things as catalysts. They turned out to be very good. And then I had the good fortune to go and study the magnetic properties, because it turns out they're ferromagnetic as well.
Wow.
And palladium isn't. Palladium in the bulk state is what's called a frustrated ferromagnet. It's paramagnetic, but in these small particle situations, it is actually a ferromagnet. So we did a lot of work with that, and I got to fire muons and probe them and so on.
Wow, really cool.
So yeah, it's really exotic, fascinating stuff. It was great. I really enjoyed my time. Unfortunately, the money ran out, and so did my job. But I had about 10 years of that, and that was great because I had the opportunity to just follow where the research went. So I learned lots of different things.
Mm-hmm. That's a great. Go ahead.
Yeah, I'm sorry for pressing this topic, but it's kind of EU related, so I guess nobody would mind. So you're saying that these bacteria were alive before you put them there, right? Or
yes.
Not?
Yes, yes, yeah. Because we'd grow up. I'd grow up a huge 10-liter culture of these things, spin them down and wash them, and then expose them to this acidified solution of usually palladium salts. I'm trying to think what the palladium salts were, but maybe a chloride or some palladium salt anyway. Just let them pre-absorb for a while and then bubble hydrogen through. So,
well, my question was because initially you said that they were dead, so I was curious how dead bacteria can retain this surface potential.
Oh, okay.
That's probably not the case, right?
No, they would be alive. In actual fact, in the situation I used, they would probably be alive because I don't know. I mean, we didn't really want them to be alive at the end of the thing, but I think that it was pretty low pH. It's hard to imagine they survived exposure to what would be fairly concentrated acids. Yeah, I should have brought along some pictures.
That's okay. I'm just searching around a little bit, obviously. So
when they absorb it, they neutralize it. Is basically.
They reduce. So basically, you've got palladium ions in solution. What the bacteria would do is they'd obviously have some site. I think it's probably an amine site or something. We had that wasn't my side of things, but basically the active site on the bacterium would reduce the palladium, so you'd end up with an atom, and then that would grow into a cluster, and then supplying more hydrogen, which is the reducing agent, would cause the preferential growth onto those seeded particles.
So basically, bacteria were acting like in acceptors of electrons.
Yes, exactly. Yeah, which is exactly how they survive in the estuary mud, by reducing sulfates.
And what do you think about those new discoveries? Maybe you've heard about it. They've discovered the bacteria that actually use the direct transport of electrons to breathe, basically. So what we usually understand as breathing is when oxygen comes into the cell and takes the electrons from whatever, like carbon. But some bacteria apparently can just feed off electrons from electric current.
I saw
basically.
that.
Yeah, I think that's an interesting thing, because when you said breathing, we call breathing respiration, but then respiration has a particular biochemical definition as well, which isn't anything to do with breathing, but actually does involve electron transport chains. So I think there are all manner of these things. I think life just finds a way. There are all manner of ways that cells find to move electrons around and harvest the energy from them. I think this is just a more direct one. I mean, the difference between these bacteria that I dealt with using sulfate and we use oxygen, there are all sorts of ways of attacking this problem. It sounds like I haven't read the article you're talking about. I've seen the headline. It sounds like that's just another approach to accepting the energy from these electrons.
And once they've done that, then how? I mean, okay. So if you've introduced a strain of bacteria into an environment to collect, say, a toxic or that you're cleaning up, then what happens with the bacteria afterward? Are they safe? Do they decompose? What is the end product afterward with the bacteria?
Yeah, I think going back to the bioremediation that people were doing before me, that wasn't work I got involved in myself, but I think that's basically just a way of scavenging the metals out of solution. And then if you do that, then you can sediment the bacteria and the metals, and then you have to do something else with it. I don't know what they do. I mean, in actual fact, I was looking at palladium, and we also looked at gold as well because of the electronic scrap. And the idea was that we might even be able to reutilize them, because, if you can get a sludge that has a lot of palladium or gold in it, it becomes quite practical to recover the metal by incineration. You can just ash it and recover the metal.
I've read about these bacteria. Sorry, they poop gold.
They what?
They poop gold. I've read about. I can't recall the name of them, but just the process that you're describing. But they eat the runoff from gold mines, and then what they defecate out is just pure gold.
Yes.
And then they collect the gold off the top.
Exactly. Yeah, exactly. That's the field that these people were working in. Exactly that. Yeah. There was
yeah, okay. Continue, please.
I was just going to say one other thing on that, a fascinating thing. There was a project being proposed. I never knew whether it came to fruition. Somebody was actually talking about getting the mud from the gullies at the side of roads, because they'd worked out that there was enough platinum from the catalysts in there to make it worth trying to recover the platinum, recycle the platinum from the dust that washed off the roads.
Wow.
Came out of car exhausts, washed down the drains, and then you get these trucks that go along and pump out the gullies. They worked out there might even be enough platinum to make that a worthwhile exercise.
Huh. That's neat.
Yeah.
Well, this is probably...
Is there any of those? Are there any of those processes that are in production level today? I left there in 2012, so what are we talking about, 6 years ago? I doubt it yet, but I think it would take 10 to 20 years. There'd probably be a couple of projects before they went. I mean, I was working with people who were making small-scale reactors to recover the gold and palladium. I actually was doing talks at demonstrations of these rigs.
they were just mini reactors. I mean, there were chemical engineers and biochemical engineers who worked with me, so that's what they did. They made these rigs, and we could put leachates, acid leachates in and recover the metals from them. The question is then whether it's anybody wants to take it upscale.
Right. Always the economics of it, of course.
Yeah, exactly.
So I just wanted to add before that it kind of makes you think about that maybe some of the mineral deposits of, say, precious metals on Earth are biological in origin, actually. This is a kind of a wild idea that I had, that maybe, bacteria actually collected all this stuff together or something.
Yeah, I think that's quite likely, yeah.
Would you say... Oh, go ahead.
And using bacteria to mine is also an area that people are looking at. I think that's one of the things why the mining companies were interested, because apart from bioremediation, there's also how do you get more metals out of a site where the economics have changed so that it's not worth mining them in a traditional sense. Can you send in the bacteria, to get the rest of the deposit out, that sort of thing?
Did you see in the process? There's the traditional, as you would be deeply exposed to, because I end up being like on the surface seeing things. But is there any indication that there might be like a transmutation of quote unquote elements or atomic configurations?
Funny thing is, this is the sort of thing we would talk about, but you'd never get to the point of putting that sort of thing into a proposal.
Right.
Because well,
because it's against the narrative.
Well, there is a story of that. I met, not quite on those lines, but my research partner was a Ukrainian, and she'd been in the group before I had, and she'd already been looking at these particles before I came along, and she was the one who discovered they are ferromagnetic. And she couldn't get this published because the dogma said, no, palladium isn't ferromagnetic. Check your results. And she was just frustrated by editors. Check your results for years and years.
Really?
Until some Japanese guy who with a more reputation in a nanoparticle group came along and said, hey, look, we've made ferromagnetic palladium nanoparticles. And my friend Irina, she'd found that 4 or 5 years before, but couldn't get it published just because she didn't have the clout. And the physicists she was trying to ally with were too timid to go ahead and publish. But so.
there was a piece of news maybe a couple of years ago about how some group made a presentation in Switzerland, I believe, or something, about how they've supposedly invented a method of transmutation with the use of bacteria. Exactly. But I actually have searched for their papers at that time, and I haven't found any basically clear statement that yes, our bacteria actually does change one element into another. And of course, it's actually a shame we don't have Ido on this discussion. He would have liked it, I believe. But anyway, my point was at that time that the energies that you need for transmutation are like 6 orders of magnitude higher than the energies you have in the living cell. The chemical energies are a couple of electron volts maybe. But you need a couple of mega electron volts in order to, achieve transmutation.
Then you'd probably you'd say, but what about LENR, the low energy nuclear reactions that they talk about in cold fusion?
Yeah, well, this is exactly the topic that Ido Kale, Edwin Kao is working on. He usually participates in our discussion, but today he has some other stuff.
Yeah, to do, so. It's a shame. Shame. I'd like to wrap heads with Ido on a few things. Yeah, I mean, we all have overlapping interests. But yeah, cold fusion was something that fascinated me a while ago, and it's just an idea I've parked over there. It's clearly something that ran into the hot fusion people and got hung out to dry in public. But really, there is something there, isn't there, with the LENR? There's something.
Are you a member of the Structured Atom Model group on Facebook?
I'm not. No.
That'd be a way to get a hold of him. You know, he runs that page.
Yeah. So many groups.
Right. Yeah, we could have you definitely have you back on at some time when he'll join us. He's certainly an active participant with us.
Right.
Oh yeah.
So anyway, kind of discussing this, the possible mechanisms that might be involved if this is correct. We've actually had this discussion before with regards to Sapphire. You probably heard that Sapphire project seems to have got the atomic mass of 3, kind of sort of helium stuff out of hydrogen.
That was just Montgomery Child's talk, wasn't it? I think I just watched it yesterday.
Yeah.
He was talking far more. I mean, he had about 10 or 12 different atomic weights, didn't he, there? They were talking
maybe.
Yeah.
So anyway, we've discussed this with Michael Clarage like a year ago, one of the Sapphire guys. And I've had this idea that, although one particle, like say electron, in their system might not have enough energy to fuse one element into another, but maybe there is some sort of, coherence where you have multiple electrons adding the energy together and giving it to a proton, for example, for it to achieve fusion, So maybe there is some sort of, I don't know, weird quantum effects or something like that acting for this to happen. Because they have a very peculiar environment in Sapphire, this plasma double layers, whatever. And it has been shown in some of their research that, these periodic potentials, such as might occur in these plasma double layers, might actually enhance the probability of quantum effects such as tunneling. So you can just, skip the energy requirement, basically. Or maybe, again, quantum coherence or something like that. So I was curious, maybe in the biological systems also something like that is possible. Because we don't know yet what role quantum effects play in, the living cell. So who knows? Maybe it actually has some internal way of, keeping this quantum thing going. So yeah.
It's really interesting that you touched on that, and I hadn't even thought about this. But people who see me post around the groups will know that I'm one of these. I don't believe in electrons. I have a lot to say. I don't believe in the electron particle at all.
I'm right with you there, actually. So you got nice support on that.
I know this is a popular view around here. This. I was trying to think what I was going to say there. Looking at an electron as a wave, it's possible for a lot of wave to impinge on the same point at the same time. So yes, if you had a high density of charge in an area, I think it's very possible that you could achieve these things at relatively low energies just because of some kind of confinement or concentration of charge. I think that's really realistic. Yeah, and the same applies to Sapphire as might to a biological system. I hadn't even thought of that. I think it's really just some way of concentrating charge, or I think a lot of it's another discussion, but I think a lot of what are called quantum effects that are considered to be instantaneous are actually not instantaneous, but they're extremely quick. And I think time has a lot to do with quantum effects. I think maybe the photoelectric effect. It's been shown that it's. I need to introduce a guy. Actually, I need to promote a guy called Eric Reiter, who has a lot to say about these sort of things. He's not really in the electric universe community, but he has a lot to say about electrons not being particles. and how some of the original papers on the photoelectric effect have been kind of glossed and slightly misinterpreted to make things look one way when actually they're another way. He says that the photoelectric effect is time dependent. So, yeah. Yeah, that's the sort of thing. It's gorgeous.
How do you show that? How would you show that?
Well, he has. Do you know what? People should really go and look at his work. I've talked with Eric. I was meant to talk at the UK-EU conference on Eric's work, and for various reasons, I just couldn't make it. I had to cry off. But people should look at his work. His thresholdmodel.com. That's Eric Reiter's work, and he has experiments which show throw serious doubt. Thresholdmodel.com. Yeah. Let's see.
I'll just try this one. There we go.
There it is.
Right? Yeah.
That's him. There is some great work on here. He's a very bright physicist. Eugene is he's above my level, probably somewhere up with you.
I think I saw his videos actually, and I've commented on Facebook to somebody about them. But
me, probably me.
Yeah, might be.
Yeah, because I'm one of his greatest advocates. He is. I mean, I'm reaching the limits of my physics to talk to Eric, but I think someone with your more solid background could probably have a more meaningful conversation with him. One of the things that sadly hasn't happened, or maybe we just haven't heard about it, is nobody will try to falsify his experiments. He basically says that you can get two detection events from what you consider to be one photon, which defies conservation principles. And I think we talked about...
Or our definition of a photon.
Exactly. Well, exactly. That's what he's saying. Either conservation principles go out the window, or you have to discard the photon. That's what he's saying, yeah. Precisely that.
Well, if you can measure the energy precisely, then and I mean, if you get the same energy for both events.
Well, he does. I mean, his... all credit to him. He's tried to pick holes in his own results. He's been doing this for 20 years. He's pretty fastidious about it, and I can't see what he's missed out. The only thing I don't know is the chemistry of the scintillation detectors, much whether there's any possible issues there, but really it looks like he's falsified the photon as far as I'm concerned. I'm pretty convinced he has.
By the way, like a year or two ago, I remember you wrote on Facebook that you are taking classes in physics.
Yes, that's right.
Can you tell a little bit more about that? Why did you do that? What did that result in?
I'm halfway through a degree now. I've had to suspend studies because of the stuff, just personal stuff going on. But I started on this physics degree. Keen to learn the methods, pick up the maths because my maths wasn't good, but also skeptical about the assumptions. And it was very interesting that every time I ran into an area where there was an assumption, to do with the wave particle duality, for example, I couldn't get anybody. I said, wait a minute, how do we know this? Isn't this just an assumption? And it was just silence. This is an online course. Just silence, nothing coming back. So, for example, you have, the double slit experiment. Say, for example, they say you fire a single photon at the target. Well, how do you know there's a photon traveling to the target? You've emitted a quantum from whatever the emitter is. But how do you know there's a photon traveling towards that slit? Because you can't see it. And the only way you could possibly see that photon is to stick something in the way that's made of atoms. Well, atoms are quantized. So how do you know that you're looking at a property of the photon and not a property of the detector?
Yeah, I would say that wave-particle dualism is not even like a theory. It's just a statement that we don't understand something. You know, we have two separate, logically incoherent between one another theories that everything is a particle and everything is a wave. And but what it is, like in reality, like sort of objective reality, we just don't know. We just apply either of those two, you know, pictures of the world, whichever fits to this particular case.
Yeah, I agree. I mean, I think the particle end of things is all assumption. You know, because there's an assumption about the emission event and there's an assumption about the absorption event. The interesting thing about that's why it's called threshold model that Eric talks about. He goes back to Planck's original threshold theory, which is that Planck thought that an atom could fill up with energy and that it reached a threshold where it had to undergo a quantum change, as opposed to it having to absorb a minimum to undergo a quantum change. So the threshold model states that Planck's theory says the threshold is a maximum, not a minimum. So, you know, you can imagine an atom has, and you're talking about metals as well, don't forget. So you're talking about bands and extended conduction systems and so on. But the idea is that the solid, the detector, could absorb a certain amount of energy and could be nearly full. So that then all it would need would be for a little bit more energy to impinge on it, and you'd get a detection event. Now, the detection event, where that occurred, would have to do with the state of the detector. You know, maybe there's one atom that happens to be on some phase of a vibration that makes it just ready to go. And so if the event happens just there, well, that's something to do with the detector. That doesn't mean a particle electron arrived at that point. That's the argument.
Well, I don't think this is forbidden by the regular quantum mechanics. I mean, we have processes like, again, multi-photon absorption, like one atom might absorb two photons simultaneously. And I can actually see how, for example, in his experiments, a photon travels, hits one detector, then gets like, I don't know, shares a little bit of its energy with the detector and travels farther with some less, you know, energy value. But then the atom from the second detector absorbs this photon, and although its energy is not enough for detection anymore, it can absorb this photon plus some other photon from the environment, like, you know, the infrared photon just from the heat of the environment or something like that. So they together would trigger the detector or something like that.
I think that's a possibility, and in either case, whatever happens there, it undermines the idea that the threshold is a minimum. So and what you said at the beginning of that comment, I think, is an interesting point, because the actual formalism of quantum mechanics doesn't say anything about particles and waves particularly. It's like the metaphysics and the assumptions trying to make sense of quantum mechanics that turn it into this counterintuitive thing. You know, I think the experimental results obviously stand. They are the experimental results. It's the interpretations that are leading to these strange interpretations, and then you get all things like multiple universe theory, yada yada yada.
Right.
I had an interesting idea just now, how, you know, speaking about this wave-particle dualism and quantization, it kind of reminds me of our electronics, actually. How, you know, we have analog electronics where, you know, the parameters change in a continuous manner, but we also have digital electronics where we have, you know, step-like functions, basically. So it's just a philosophical digression, basically.
Yeah. Well, no, I think it's very relevant as well, and it allows me to introduce another big name. Are you familiar with Carver Mead? Do people know Carver Mead?
I don't think so. I haven't heard it.
He's known as Chip Daddy. He's one of the original greats of Silicon Valley. I think he's in his 70s, probably 80 now. There's an interview with Carver Mead. I can't remember whether it was Science Magazine or one of these. If you look at Carver Mead interview, you'd find it.
I might be having a connection difficulty here. Bear with me for a second.
He's the guy who invented very large-scale integrated circuits. So that's him. He doesn't think electrons are particles. He thinks electrons are waves. And this is, we all know that an engineer's take on things, carries the burden of proof. He's
right.
Looking at that. Yeah, he's a great figure. If you look at there's a fantastic interview I recommend anybody read. He's an awesome guy. He does some very interesting talks as well.
Yeah, definitely.
Yeah.
Is he still up there and active?
He is, yes. I think he's a big. I don't think he's working. He kind of is like a charitable institute type thing now. I think he's working, promoting science and engineering and being. I nearly said, what do you call those people?
Luminary.
Philanthropist. That's it.
Philanthropist, yeah.
I nearly said an anthropologist. I knew that wasn't right. Yeah. Yeah, I think, but he still actively talks, although he's definitely getting on. But he has a great beard too.
Very cool.
Yeah. Oh yeah.
So I mean, the theme of the non-particle electron I find really compelling because it's a radical, quick, if you like, meme. The electron doesn't exist kind of thing, and it's like, what are you talking about? And then to be able to back it up,
Well, this is something I wanted to tell Edo about actually, because Eric he says photons don't exist because of his work, electrons don't because of his work, and alpha particles don't exist because of his work. Now, what does that say about
the entire structure, right?
Yeah, the entire structure of a nucleus. And I have friends who I've talked to. I liked Edo's model. I invested in magnetic balls, huge quantities of them, when I saw his work, and I started, trying to assemble those structures. And it was very interesting to see how a magnetic ball bearing will only go in certain orientations as well. And if you I think that the idea of protons as toroidal vortices might be a feasible idea. Well, then a magnetic ball bearing would be a good model of a toroidal vortex because it actually is carrying that magnetic structure in it. So anyway, I just thought that was a compelling model. But then Eric says, well, you can get this the effect that he talks about, the unquantum effect, with alpha particles as well. So yeah, I don't know.
This is where I start getting it's these fundamental ratios and then harmonic relationships, and that's what talks to me at least.
Well, you'd like Eric because Eric talks about the ratios. That's what he says. They are the things that are true. He says the ratios hold true. Nothing else seems to. Yeah, he actually wrote about that. So I recommend you might like his work then.
Yeah. The one that's come through for me is Richard Merrick. He talks about interference, kind of morphology through interference and combinations of ratios of waves, etc. It's a big rabbit hole, of course, but. In gifting back to you, I would say he's worth at least a scan of his work.
Richard Merrick.
Yeah, here I'll put that in the chat.
I'm gonna put him on my list.
Yeah.
List of things to read.
Yes. Yeah, because I don't have anything.
Yeah, he's in Texas. He's a computer guy as well, but then also pretty what's deep study musician. So I mean, the combination of those two. So the things that happen within the octave, I think, are kind of left off.
Okay. Well,
it's once again phi ratio, but where constructive interference occurs, and then how that relates to morphology. So.
And by phi, you mean the golden ratio?
Mm-hmm.
The most.
I was actually kind of thinking about the thing you mentioned once, David, about the how some guy claims that irrational numbers do not exist.
Oh, right. The hyperbolic, yeah.
Yeah, I was thinking about it, and I actually like this idea. But you know what? That the phi or phi is actually the most irrational number.
I know, exactly.
Yes.
That's
so it kind of does not exist to a perfect degree. Sort of.
Right. Well, it's the infinite regression that you have to do.
Yes, exactly. But I mean, you need arbitrary irrational number. You have this degree. This infinite regression that can be approximated somewhat, because in the denominator you have. Well, it's kind of difficult to explain with words, but anyway, with phi, what you have is you have ones everywhere.
Yeah.
Denominator. So it's the worst possible. It's the worst number to approximate to.
Right. Right. I mean, the one that comes through is it's the catcher. It's the catcher of the light. Ultimately, if you want to go really out there, right?
I don't quite understand it. What do you mean?
Like what you do,
like a cornucopia.
Kind of, yeah, like a big, like a crazy. Yeah, this is how things material. There's an idea.
Perfect black body, right? Or something like that.
Exactly. And this is what they did in the a lot of times when you design acoustic rooms, etc. It's the golden ratio. They've done this throughout history in order to absorb the sound. So it's an interesting, at least, theory to put out on the table. Yeah.
So. That would tie back into Richard Merrick's octave theory, I guess, wouldn't it? I mean,
right. And what are it's also intervals, how the intervals relate.
Yeah.
And I've studied electrical engineering, and I was always like, this is really interesting what goes on within the octave, and we never studied it. Harmonics were always, for the most part, just multiples of the frequencies. And it's like, well, it's all happening in between there,
Well, the multiple of the frequency phi is phase conjugation. So that's like what you were explaining as the catcher, as phi being the catcher of light, because phi is literally, it's almost like the ineffable. It's the indescribable, therefore it allows for variety and the largest amount of variety, because biologically, and I mean, if you think about it, it could be the recursion that just allows for there to be creativity or choice inside of light as well, on like a neural level.
So just infinite recursion kind of idea, at least.
What is the musical? Yeah. What is the musical?
In your brain and everything.
What is the interval of phi in terms of music?
Often referred to as the tritone. I mean, it's got an interesting history to it.
It's not a tritone. It's a bit bigger than.
It's like a sixth. Yeah, okay, but the base relationship, if you go from the minor, like the root minor, up. There's different ways of looking at it. Yeah, there's different ways of looking at it. But I think for me, at least at this point of my looking at it, it's the fact that it's the most irrational, like you were saying.
Yeah. But you know that our equal temperament system of notes is not directly derived. I mean, it's derived from these natural tones, but it's a bit adjusted because you have this in the natural sequence of sounds. You have this wolf fifth.
Yeah, Procrustean fifth.
Maybe, yeah.
Yeah.
So it has to be adjusted a little bit.
I did that one time. You take the cycle of fifths going up with the frequencies, and you would think octaves match, obviously, right? But fifths don't.
Huh. I know.
And it's 12. It's you know.
Yeah, and if you, I mean, the fifth is basically the most important step in European music, at least. It's the dominant. Basically, the second most important, aside from tonic.
Right.
European music. What did they ever invent?
The three halves. It's like 3 to 2. You know, 3 to 2 is the.
Yeah, well, if you look at you know, blues and stuff, it's also all based on the same premise, on the same 1-5 relation.
Yeah.
And actually,
I mean,
I would say
1-4-5 is really 2-5-1. Right?
2-5-1 is a jazz.
So it's 5
standard sequence. Yeah.
Right.
You guys might as well be talking about Actually, I know more about computer programming than that.
I love music, but I don't understand any of this.
I'm like, that's the one that makes me go like this. Oh, yeah. That one makes me move real funny.
It's one of the most used blues tones. You know, the flat 5, and it's like that's the one you've heard it 1,000.
Oh, I probably have. I mean, the moment you just go, no, it's this, and just played it, I'd be like, oh, you know, because I you know. But I don't know the descriptions the way that you do. I'm happy that I know what chords and bars are. So, I mean, I was really good on the recorder in grade 4. I'm just saying, but that's all I know.
Grade
I'm wondering
4?
how
that's the last time I touched a musical instrument. Probably grade 4.
I played trumpet in grade 4 and really was no good at all.
I remember playing Born Free on the recorder.
On the recorder? Oh my God, those things were great. And I understood, like, but I just pianos were better for me. I could understand them better.
Yeah.
Well, you hit this hard and it's loud. Hit it soft and it's not as loud, but here are the notes. You know, it's all laid out.
There's a guitar virtuoso, Yngwie Malmsteen. Maybe some of you heard about him. So he says that he loves piano because
didn't he play in Dawkins?
It's just kind of perfect. You can just, he says, you can just throw a cat onto a piano and you would get music, basically. You don't have to do anything specific.
I was at the Toronto Science Center. I couldn't have been much older than 14, and back then it was high tech. I mean, I went there and saw a giant laser, which I thought was really cool. You know, but they had this keyboard that they said you could, because of the way the keyboard is laid out and the way the computer or whatever's inside of it, because I didn't know at the time, it was a big circular keyboard that anyone could walk up and just push on. It would just make music if you just started typing notes. Like it would know how to make this melodic. You know what you're typing in or what the keys you're hitting. I thought that was brilliant.
Right.
I'm sure that must still exist today.
GarageBand. Yeah, there's a thing called GarageBand that has you can choose. They've analyzed all the different jazz sax players and different Miles Davis, etc. But they've analyzed this. I'm not a supporter of the whole idea of AI, but this is as close as it gets to me to AI, where they get like the ideas that they would do in their improvisations. And it's really compelling to listen to. You can run, here's the chord changes. How would Miles solo over this? And it runs, and it's pretty close to how Miles would solo on it.
Oh,
you know?
Well, that's actually pretty cool.
It's like,
So I looked into the tritone in terms of frequency, and you would get actually, if you take it upwards, like multiply the frequency by 1.6618, you would get something in between a minor and major sixth, actually.
Yeah.
So
right.
if you take A,
right.
If you take A as the tonic, you would get F or F sharp, something in between those.
Mm-hmm. See.
But if you take it down, like multiply the A frequency by 0.618, you would get something in between major third and a perfect fourth. So it would be in between C sharp and D. So again, it's pretty consonant, I would say. It doesn't sound like a tritone or whatever. I mean, sixths are okay, and thirds and perfect fourth, and yeah. Yeah,
this guy has gone much deeper than I've gone into it, but he relates the phi relationship certainly to like tritone substitutions, which is often done in a replacement 4251, which we were talking about. So, and then Pythagorean tetrachords. So, this is as far down the rabbit hole as I've gone. So I just know I tend to be like, it feels like I'm like a terrier. It's like I'm pointing in a direction, but I don't know the answers yet. But it's like I have the scent, you know. So, but there's certainly something here, and Buddy's definitely pointing at this as well, you know. So that's what I see.
Yeah, it seems like the whole structure of everything that I'm, from the perspectives I'm looking at it, is phase conjugate. It's almost like everything is cavitating. I would say all things are cavitating, and electricity is vortex-based, and it's the vortexture surrounding the objects that are like the interior of the atom, almost like a surface tension around something that is sort of there, and a projection of the center. Sorry. The electron seems like a cloud, but not just necessarily a cloud. And I don't think it has to be a wave or a particle, because there's things that, what would be a wave and a particle? I think something helical would act as both wave and particle, because if something's helical, then it has a node, and it also has the filament-like structure, because it nodes up as it reverses its spiral tendril. But yeah, I mean, to me, it seems like if the sun is cavitating, and the black holes at the center of all galaxies are cavitating, then all things are cavitating, and growth and the living structure of existence comes out of this cavitation. And the Earth is expanding. We are sucking in outer space. Everything is sucking in outer space. If we're mostly made of space, then space is moving through space is what's happening here. But this space is being harmonically composed and harmonically decomposed constantly, because the last moment was decomposed. Everything from that moment doesn't exist. And the future, nothing exists. So there's void in the future, void in the past. And we exist inside of this vibratory, sort of like filament-like living structure. And I wouldn't call it a simulation. I don't believe in the simulation hypothesis. And the whole thing inside of its cavitation happens to be phase conjugate as it moves, which is multiples of golden ratio, and that's what I'm discovering. And I built a little
when you say phase conjugate, how would you define that?
I would define it as like a pine cone. Phase conjugation is the recursion of phi on all levels, on all scales, and basically it's sort of like the wind through the channels of all frequency, waves, and vibration, and how logarithmic waves and logarithmic scales are built, because if you look at existence, it's clearly logarithmic scale invariant. It as it changes, it stays the same, but it's constantly changing. So there's a logarithmic scale invariant that we see and we perceive from all of our senses. Every single one of our senses detect reality in a logarithmic scale invariant manner, because reality is built in a logarithmic scale invariant manner. So that's why we perceive it, because it happens that way. And of course it's fractal, and then I could go on and on about how it's filament and nodal in nature. But I think all theories are partially right. And in a way, there's a lot of theories that are partially right, but
right. The challenge is always how to get it coherent, so it's something that people can put, have a foundation on. So this is right. Always our challenge, and we're getting there for sure. If you look at it from the start, we're a lot less chaotic than we were at the beginning.
Well, the logarithmic nature of things is actually well recognized. I mean, probably the most important number in physics, and probably in chemistry, but I'm not sure about that, is Euler's E, the 2.718, I guess, which is the base of the natural logarithm, because many natural processes, at least our models of these, seem to behave in an exponent type of manner,
It's exponential.
Exponential, yeah.
Yes, everything is exponential, and that exponential expansion is what makes me derive the idea of it all cavitating in unison. It makes the most sense if you think about what cavitation is.
And again,
this is where we're getting this, the sonoluminescence and all these interesting actions, seems to be to me.
Yeah.
This is where I'm kind of seeing that like when I said cornucopia earlier, is that V spiral, that action of the spiral scalarly growing as it comes out, and it also being able to refract at each point along its way. So the way it visualizes to me is like that sound, the waves, the vibrations create refractions of light that get trapped, and they're solidified because the waves are intersecting in ways that don't allow the light to move. So that light then becomes solid. It becomes fixed where it is in that point. And the scalar progression of that allows for matter to be built. So the light is trapped by the intersecting sound waves, and it grows in a helical spiral manner. But I still have a hard time with the visualization of everything being helical, simply because there are things that are not. So I
the fundamentals.
I see that it's recursion. I understand what you're saying, but at the same time, it is a variant. It is a possibility. It is everything. Because so there's trihelix, where there's 3 points in the helix, there's 4 points on the helix, and then also like I can see the string of bands, but then they become these geometric, 3-dimensional geometric shapes that may also be stuck to some sort of helix. But if you break it down into like the smaller parts, they become, I said decahedrons, they become dodecahedrons, they become three-dimensional objects, which are then also surfaces to refract more light to create.
This is also a point where I miss Ido, because he has this, theory of Platonic bodies and how it relates to atomic structures and so on.
Well, yeah, I would agree with what you're saying generally, Heather, but I don't think it would be light. I think it would be. There's a part of me that wonders if there's a. Well, we know that on the atomic scale there's a collision of forces, but the forces that are involved could be, as we know, they form different patterns. As Eugene has pointed out, there's a sort of a place where the electrons will be, or what's it called there? The place where the electrons will only be, and they won't be any other place. I'm not sure what that curve is. It's a mathematical equation. I'm not aware of the name at the moment. But there could be, because of the motion of that charge or charges, and the way that they're creating some sort of harmony or resonance, and that makes the appearance of solidity. Now that I can go with. I'm not sure about the light part, because light is more of a wave that is an electromagnetic wave, sort of travels linearly. Although we can slow it down now. So
if you can break light down into its individual spectrums via refraction, how come that isn't a possibility or considered or spoken of possibility with other types of EMF waves?
I think that what you're talking about is light core samples. How and when and can we create light core samples? Yeah, break it down into its individual. And like
everything seems to be glowing. We talk about sonoluminescence. We talk about these things when these types of things interact. At the points where they interact, there's often a spark. We speak of the spark of life. We see the things light up. We see the sperm enter the egg, and there is a light. It is that entrapment of light. It is that is the consistency, right? That is the thing that seems to be prevalent throughout. And vibrations. So you have light and vibration as these two main constituents that are constants. Whenever we speak of anything of this nature, there's
light is vibration, isn't it?
Yeah, so that's what I'm asking. I'm asking about the refraction of other. I'm asking, I guess, a few things, but can we refract other sources of EMF, other frequencies of EMF? And
yes, and it's actually one of the reasons why I don't believe that gravitational lensing is actually gravitational, because like radio waves and microwave waves, they get refracted during the so-called gravitational lensing, which
shouldn't happen.
It's not exactly, and it's more of an evidence of a refraction in plasma rather than gravitational lensing. But I also have a sort of a philosophical digression on what you said about how we, decompose light into different frequencies. So it's sort of a, I don't know, how do you call it? But anyway, so when we disintegrate the solar ray into the spectrum with a prism, so my question is, are we actually decomposing it, or the prism actually adds something to it, It's sort of a kind of a, I don't know, Taoist type of question. Can you hear a sound? Is there a sound from a fallen tree in the forest if there's no one to hear it, Are we actually decomposing the light, or the prism actually, adds something to it?
Well, there's that. Yeah, there is that thought, especially when you're say you're painting a three-dimensional object sitting on top of a surface, where the darkest place of the shadow is that the lightest place meets. It would actually be the opposite of what you would expect it to be in order for it to actually give you the illusion of three-dimensionality. So the lightest, the darkest part of the top of the surface is going to be adjacent to the lightest part of the of the next surface. You understand what I'm saying? They're going to butt up next to each other, and that will give, even though there might be more light on one side than the top. This is why I have a problem. And then also when it does that, you borrow some of that color, you borrow some of that hue from it to also give that illusion, so that it's showing that it's sitting against that space. It's slightly reflecting the pink of her dress on the chair, and the chair is slightly reflecting the blue of the velvet on her dress. And then these are these interactions that are happening, and the only way that it looks believably 3D, real photorealist painting or artist making, that there has to be that inclusion of conversation between objects and the lights that they're reflecting on one another. And that's why I often have this question about what is going on that we're actually seeing, or that's bringing to. And then also, is the end of the rainbow brighter because it's reflecting from the light, like the light particles the water particles that aren't included in the breakdown of that spectrum right there. So like the underneath ones, they're shining, but they're still shining white light. So it seems brighter. And that's a great question. Is it borrowing it? Is it sharing it? Is it diffusing it? Is it breaking it down? Or are they blending and then becoming something extra?
It made me think about this internet meme about what color is the dress. Do you remember that?
Oh God, yes.
It's gold and blue.
Both sounds like a physical version of emptiness in Buddhism. You know how the existence of something is really not the existence of the thing, but the combination of all the factors in its environment. You know, how something doesn't exist in isolation, but the reality of it is just a reflection of everything else that surrounds it. And if you took away all those things, then the thing itself wouldn't exist anymore.
It made me think also about kind of what you're talking about, is that everything that we observe and that we sense is technically dead. It's already old light. And the real event is just before our perception of all things beaming constantly into existence. You know what I mean? Like
opposite. What if it's the opposite of that, and that it comes to light as soon as that it comes to life as soon as it is perceived? Because I read this awesome quote by Lenz that was talking about how often I can't remember exactly how he stated it, but that we often think that things are happening outside of us, but nothing is really existing outside of us. The only thing that we can actually perceive comes from within us, from within our mind. And we're creating everything that we're seeing, because if we didn't create it for ourselves, we wouldn't perceive it. Kind of an idea.
That's really strange perspective for sure.
But it's present not only in Buddhism, but even the European philosophical tradition has a similar approach to things. For example, George Berkeley advocated in 18th century that basically the objects are our, mental constructs created by summing of our perceptions. If we see a table, we call it a table because first of all we see it, we can knock on it, to also receive other perception, not only sight, and we hear the knock and so on. So we kind of wrap all these perceptions into a single object, So the object is kind of a secondary product of thinking rather than a source of these perceptions, at least in the way it is constructed by us mentally. And that's where you get all these illusions. When you can see objects that are not actually there, it's because your mind creates these objects from the sum of its perceptions. Although there wasn't a source in the first place, it's just an optical or whatever other type of illusion.
Mm-hmm. The thing that, I mean, the to pull back into Ito, which also I think ties in with what you're talking about, Eugene, is the rarefaction and compression, and then what's that fundamentally, like the absence of something versus the thing itself, and then how they interact in time from the smallest scale to the largest scale. So pressure, instead of having it all these different blocks that we cut them into in our mind of these are gamma rays, these are X rays, this is red light, this is purple light. It's like the entire thing is actually a spectrum of rarefication.
I believe that there's Bernoulli's principle, and I've been thinking about this a lot. And it's a principle of fluid dynamics that makes me feel like the ether works in the same manner as the principle of Bernoulli's principle, where when you add water to a vessel and you have a bunch of different size hoses coming out at the bottom, the water is going to flow equally through all of the different size pressures. There's something along that reminds me of the ether doing the same kind of things, same modality.
Well, it would only flow out at the same height, at the same level, but it would flow differently from other levels, like with different pressure.
Mm-hmm. And that's his that's basically, I guess, his principle, and it works for a lot of designing and stuff like that. I wouldn't know, but that'd be cool to get into that kind of designing.
So what do we think about the consciousness stuff going on with the EU? This kind of a sudden, at least to me, it seems like there's been a fairly significant turn of their direction over the last month.
Last month?
They've actually had other videos on that topic before. I definitely saw some of those. Like a year or 2 years ago, there was some other videos. So it's not something new to this community.
Okay.
Yeah, and it's also probably one of the few places where, I mean, there's a direct link. The people who really liked Sheldrake's work, I mean, if you just look a bunch of Sheldrake videos up, eventually you will come across the one where he espouses love for the electric universe. And that's, but he's right in the fact that the people on that side of the thing are going to think more about, more highly of his work because of the fact that we deal more or less with fields as opposed to materialism, and that we're willing to look into things like the changing of the speed of light over time and other things that he calls scientism. We're poking holes in that. So in that sense, we're kindred spirits, I guess.
Right.
So there's an occasion, like really right now, because to speak about EU-related stuff, because literally 24 hours from now, the Mars InSight lander is going to attempt to land on the red planet. Yeah, so
is it? Have we ever landed on Mars yet? I know we've been on there with rovers and stuff like that, but do we know how many times successfully we've done this?
At least 5, I think, maybe more. Okay. So yeah, and this would be, I think, the first attempt to drill at least like few meters deep into the surface. So it might bring some interesting results if it lands in the first place, you know, because the last attempt of landing on Mars was made by Europeans in 2016. It was a Schiaparelli lander, named after this Italian scientist who studied Mars. And it was unsuccessful. You might remember that it basically crashed.
Yes.
And there was a sad joke about it.
Yeah.
There was a sad joke about it that, there was a crater on Mars named after Schiaparelli. Well, now there's two.
Oh, thing.
It didn't happen to land on top of Beagle, did it?
Yeah. Well, they found Beagle a couple of years ago. But anyway, so but it's really unfortunate because this Schiaparelli lander had a specifically designed instrument to measure the electric fields on the surface. So it was really a big, a big disappointment in EU terms at least. But this InSight lander the primary objective of it, I guess, is to drill into the surface. So I had thoughts about this like a year ago or maybe more. Is in mainstream sort of planetology, there's an idea that the nebular hypothesis, first of all, and so on and so forth. So they think that the planets form from this primordial heated up state of matter, and then they cool down, and because Mars is smaller than Earth, for example, it cooled down faster. So at some point in its history, again, supposedly, it had these oceans and so on and so forth, because it was hotter back then on Mars, so the pressure, the atmospheric pressure was higher and the water could exist on its surface. But then it cooled down and yada, yada, yada. But what I think is possible, although I wouldn't bet my money on it, but still, maybe this probe that's going to drill under the surface of Mars might actually detect a higher heat flux from the interior than is expected from this idea that Mars is already a dead planet that is, super cold and so on.
Right.
So that would be definitely a serious, a big blow for the planetology of Mars as it is today. But yeah. So maybe you have some other thoughts on this, but I actually don't think it has any specific, electric types of instruments, again, to measure the electric fields, which is again a shame, I guess.
What other probes? This is the probes that are going on this thing?
Yeah, this is the lander that is going to attempt to land on Mars in 24 hours.
Depending if they got the calculations right and didn't do the foot meter thing and then plow the thing into the ground, yeah.
They got to do this.
Yeah, actually, that's
challenging.
That's something. Well, it's a lot more challenging because you don't have atmosphere. Like, right. I mean, if you're trying to land on the moon, like I've noticed a few of those things that we would never get on like some of those trails of like crater chains across the moon. We were talking about this in that one where we were talking about the Deimos's striations were made by rolling spheres or something, or which was ridiculous. But they had this. They have these crater chains, and I noticed that on Earth you're going to have to go through that great big boundary because you have like such a thick atmosphere. Then once you discharge that, it's going to be one big pow. But if you had no atmosphere, the thing could be coming in at like 36,000 miles an hour and won't slow down right to the surface. It's just going to be going closer and closer, and it's going to go zap, 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 zap right across the border. So,
well, you see that the problem is that it actually has an atmosphere, but it's very low density. So
well, true.
It kind of
Mars is thicker. I meant the moon, but yeah.
Yeah, it's thick enough to cause problems for you, but it's not thick enough to help you slow down. That's what
it's the worst type of atmosphere. It's only a bad atmosphere. Yeah.
So you can land on the moon pretty easily because it doesn't have atmosphere, and you can ignore it right away. And you can land easily on Earth or Venus because they have very dense atmospheres. And you can slow down just by using those. But on Mars,
like those,
you have something in between, which is a big problem. And actually, only the U.S. probes so far made it to the surface. So again, this Beagle probe that Neil mentioned failed. It was, I believe, made by the UK or maybe the European Space Agency. And also this ExoMars, which was also made by Europeans with collaboration with Russians. It also failed. I don't think there ever been successful landing attempts of anyone other than the Americans, which gives us hope because this lander is also NASA's, so maybe it would make it to the surface.
Oh, NASA's doing it because they can fake it. I'm just kidding.
Is that why? Kubrick is still alive.
Kubrick's still alive, yeah.
Yeah.
No, that's... I noticed they were putting a positive and a minus on that. Were they trying to imply that there was a positive-negative situation?
Oh, I don't know. Where was it?
Yeah.
I like that. I like the
little pluses.
That's cool that they do that, right? Of course. Yeah.
That's actually pretty cool, yeah. Imagine how tough that thing must be to be able to survive that. I like their ideas, like some of the stuff that they had, like, doesn't matter how it lands, we'll get it on its feet, cover it in full of balloons so it can roll across the surface, Thruster jetpacks, which one are we going to use? Yeah.
Yeah,
well, at least they're drawing comas. Oh no, they just have little pluses there. No big deal. Don't worry about that.
So, any ideas about that?
About which part exactly?
Well, what it can find, maybe.
Well, it's interesting that it says that it's also looking to chart its tectonic activity when they hit the dead planet. So, maybe
well, yeah, but
it says from the image said tectonic and then specified differently, like surface vibration from being hit by meteors.
Did they show where the tectonic boundaries would be?
Well, they do think there's one right around the planet. They used to think that back in the old days because and I know this is really strange, they thought that somehow one side of Mars was managing to fall into the other side because of that, and then they eventually turned that into a giant crater.
I think that
hemispheric crater. But
I think that Valles Marineris is supposed to be like a tectonic rift or something. No?
Well, they have no other mechanism, but so that's what they're falling back to. Yeah, but plus it can't be an outflow because it's deepest in the middle. So
right,
things like that. I find Mars to be like the more that we research Mars, and the higher the detail. I mean, it should have already happened. I mean, we should have already said, like the electric comet should have been a big proof. But seeing the high detailed version of Mars and seeing the clear demarcation of a wonderful strike and those anode blisters right there, and that half of the planet is thinner than the other half of the planet because it's 3 miles lower on the north part than the south part, and it's filled with little scallops. I mean, all of that indicates to me, see, they're doing that wrong thing with the friggin' things.
Yeah,
see, I'm getting all Jan Lampert in
Sorry
there.
about it. Yeah.
Arr.
I mean,
but
that's all I have access to.
It's okay. It's okay. You're doing great.
Oh, thanks.
But yeah, we don't know what's really inside Mars, and we don't even know if our planet is unique only because of the water. Is it unique because of this atmosphere allows, because we know that there's electrical activity on Venus. I mean, we know that the sky is just lit with an aurora underneath the clouds. So we know that's true, but that's not the same thing. Mars apparently is dead with a few active, like dead volcanoes, they call them, those Olympus Mons and friends, the Tharsis Bulge. But we don't know if there's actually any seismic activity. Is it just a simple rock, you know? Like,
are you sure there is aurora on Venus? Because
yeah,
it doesn't have a magnetic field.
No. It's when they sent the probes through Venus's atmosphere. I'm not sure which ones they were, the Mariner or the Viking. I can't remember. And they went and landed. It was brightly lit underneath the clouds, and they registered that they passed through an area of near constant lightning. So the entirety of the atmosphere was just on fire with lightning, but it's in the cloud layer. So I call it an aurora, but when I say aurora, I mean like a coronal glow around the whole planet. It gives off more light than it absorbs. That's why it's the brightest thing in the sky. It 30% more, I think, if I'm not mistaken.
Well, I cannot agree with it, but okay.
Well, I'm not making it up. It's just you can the pictures of Venus were taken with that light. It was a universal glow from all directions, and it's so the aurora or coronal glow is so powerful that the mountains are apparently made. They think the tips of the mountains are made of metal because they are reflecting radar waves like metal does, but so does plasma. So it's likely that the tips of the mountains on Venus are aglow with plasma as well. We just didn't see them in the pictures. So
yeah, that's actually a good point. I haven't thought about that.
I think I'm stealing this from the thunderbolts.info, by the way, because I'm pretty sure that Stephen Smith did an article on it, and that's what I'm stealing from. So congratulations, Stephen Smith, wherever you are, if you're watching.
Well, it's also very hot on the night side too, right? It's still like
it's hot on every side on Venus.
Large amounts. It doesn't cool off. Right.
In fact, you can't. If you landed on the night side, you couldn't tell it was night because it's so bright. I mean, it's like literally the sun doesn't reach the surface. The light that you're seeing from the pictures of the surface of Venus are all from that glow. And if you notice that there's no shadows or anything. It's like, yeah, you're looking it up. You'll find it. Yeah, these. It's a glow from every direction. It's just a universal glow in the sky.
They got a bear trap there.
That's how you catch bears on Venus.
Yeah, you got to catch bears on Venus.
It's like the North Pole. They're big bears. Yeah.
Yeah.
Just go with Venus, it. Just slide that in.
With Venus, by the way, the situation is reversed with respect to landers, because I think only Soviet probes landed on Venus. Like the Americans did never even attempt to do that, nor did any other space agency around the world.
Oh no, they only lasted 15-20 minutes tops. That was it. They that lander right there is called the Vestas Venera. Okay, so it came down and it was made so strong that the lenses that we're looking through here are made of diamonds.
Wow.
Because nothing else could take the heat. So they polished a diamond lens to make a lens for this thing. And that was what... And remember, this is equivalent to being under 50 atmospheres of water right on that surface. Like something 50 or 80, something like that.
I think it's 90 atmospheres.
Oh, see? Anyway, enough to crush us into little tiny pieces of goo. So, but yeah, and that's just the air. That's just it's. Could you imagine air that thick? Wow. But yeah, we would. It looked pretty amazing. And of course, the cool thing is, it's the rocks everywhere. See, like just fields of rocks, just like on Mars. Like, where do these rocks fall from? Like, come on.
Yeah. And the winds are pretty slow because of the super dense atmosphere.
Yeah, probably best call them currents or something because they're so thick. Yeah. Still, and of course,
What
one
was
of the
the year
reasons
that they did this?
75, I think.
Wow.
I'm blown away by some of this when you think about it. And that great big scar all the way around the middle.
It's wild.
Like it's a big birthmark all the way around the whole thing.
Yeah.
This is why a lot of people are wondering which, like, did it come out of Jupiter? Did it come out of Saturn? You know?
Mm-hmm.
Because it has, everything's
big
brand new
here.
and fresh, it looks like.
Right. But I mean, look at what happened there. Yeah.
You know what's interesting is that other bodies also have this equatorial kind of. Again, looking at Mars, we have Valles Marineris, and also we have this similar valley on Titan, in the equatorial region, and also on Pluto.
Huh.
It kind of makes me wonder why we don't have something like that on Earth.
Maybe we do.
Yeah, well, maybe it's also because the capacitance of the planet spreads the charge around when these ones aren't doing that, so they're taking the direct hit in one spot, right?
Well,
But on the other hand,
More too.
on the other hand, Mercury also doesn't have something like that. So maybe these planets just come from, different groups or something.
well, those two planets and Titan would be like this. I mean, if Titan was one of those bodies that was just recently captured, it would be very Venus-like if it wasn't orbiting Saturn. So, if we can envision then that these three bodies were three of the bodies that were playing games, that could explain why they were having hits, because they were, I mean, Venus and Mars fought each other. Jupiter apparently got blasted by Mars. That's what caused Hephaestus to get the scar on his face, and yada yada. Here's the Mars thing. Venus could have easily been captured by one of those planets on the way out. It could have been one of the players long ago, like I don't know, some other god that we assumed is now, we thought was Mercury, but maybe it was, maybe it wasn't Mercury, maybe it was Titan. We don't really know.
Doesn't Mercury have a magnetic field?
A weak one, yes.
It does. Yeah.
Weaker than ours.
And Mars and Venus don't?
Venus does
don't.
not have
No.
one, no, and Mars has crustal areas. That's it.
So
And-
that's okay.
Yeah, I just wanted to add that I said that there's probably no aurora in the sort of, usual sense of the word on Venus because it doesn't have a magnetic field. But there is definitely aurora on Mars from this weak surface magnetization. And it has been observed, at least in the ultraviolet, by MAVEN spacecraft.
And we still see transient lunar phenomenon on the on Moon, obviously. There's been more than one. There's been a few stories about what they saw on the Moon, like just a few thousand years or just a few hundred years ago, when they saw a big impact on the Moon and a big flare up, and it looked like it had wings and stuff, and then it went away. Like, because the aurora was bent, and then it was, not bent anymore. But
if a charged body did run into the Moon, would that effect be able? Could it possibly have been created from the object and not the Moon itself?
Oh God, yes.
Like the charged particles have just been so it's likely that may not have been the Moon that was actually glowing like that. I mean, the cause of it, the Moon itself wasn't suddenly, or you understand what I'm saying? There was the charge, the glow came from the object. The object brought the glow with it. So the Moon doesn't really have it. The Moon is reflective of all light and charges, like the Schumann resonances and things like that come off of it, but it doesn't inherently create its own of any kind, does it?
Well, any time that a sufficiently charged object approached the Earth, like we were talking about this when during the Tunguska blast there, when that happened in 1908, for a couple days beforehand, the aurora was extremely strong. And this what I would envision would be happening as the body crossed through the magnetosphere and began its approach to the Earth. and it began to affect all the magnetic field lines, we'll call them. I know that they don't exist, but you know what I'm saying. And they are obviously generating auroras. I think the same thing would happen to the moon if something was coming close to it and it was sufficiently charged. It doesn't have to be incredibly charged, but enough that it would push the boundaries of the aurora to go from dark mode to glow mode for just a few minutes. You know, so that could happen. It should happen on probably every planet. Anything that has sufficient charge should cause a reaction like that. And since all planets seem to have charge, at least some, so it's relative, right? So
we've seen one such occasion recently, like in 2015, there was an encounter between Mars and the comet Siding Spring, like literally 3 years ago or something like that.
I heard that, but I didn't know if that was actually. Yeah. Some people were talking about, it was fake, it was real. I didn't know what to make of that. So.
No, the encounter was real, but some of the people claimed that they actually saw a discharge on telescopes, but that was an incorrect interpretation of what they actually saw. But anyway, there was a few papers published after that, which kind of accumulated the stuff from the spacecraft that we have there that measured stuff during the event, and they found that this comet actually deposited kind of much more material onto Mars than was expected, and it actually created basically a second ionosphere around Mars. So it was another, I think it was positively charged, another layer of ions, either from the stuff that come from the comet or maybe from Mars itself, but somehow ionized by the comet. But I believe it was from the comet. Yeah. So it was a pretty significant event. Yeah,
that is pretty awesome, actually.
Yeah, and it wasn't even a close encounter. The comet only passed within like, I don't know, maybe tens of thousands of kilometers from the planet. So it shouldn't have, any major effects on Mars, but it did really create a significant atmospheric electrification, so to speak.
I think the same thing happened to the Earth there. We talked about a CME came, and I think it was on Michael Clarage was doing a talk probably in 2015, 2016, and I recall him discussing how the planet would normally has one ring, the ionospheric torus around the Earth. But then when this happened, it gained a second ring, a bigger ring to the outside, basically another shell, if you would. And obviously I could envision that happening on Mars as well. So.
Well, that's why though that I posted that, because today is the anniversary of Comet Ison. Making perihelion, or not surviving it totally, but there was a lot of buildup to Comet Ison because of the effect that it was having on planets and the surface of the sun from extremely far distances. Like once it came out by Jupiter,
didn't it get big?
The shape of the comet was becoming coronal holes. Like coronal holes were reflective of the shape of the comet, and the sun was extremely reactive to the incoming comet. And every time we have a sun grazing or a sun diving comet, there's an ejecta out the other side almost instantaneously as the comet hits the sun. This thing was pointing and spitting and shooting months before, and then we were supposed to see it on its return out, but because it disintegrated after perihelion, we never got that. The dust from it was so fine that it didn't even make a meteor shower for us to go through.
I should note that I've studied this phenomenon of suggestion that the comets may trigger CMEs, and I can tell you definitely that not every comet provokes this solar activity. But again, there was another peculiar case where an external object did provoke an activity, and that is this interstellar asteroid Oumuamua that came its perihelion happened on September 8th, I think, or 9th, 2017, so it was almost a year ago. And at that time, we've had a sudden spike in sunspot area, and later, actually, the strongest solar flare of like in 12 years happened, like X 9.3, I think it was, on September maybe 10th or something like that, or maybe 6th.
Right.
But anyway, so I've made a couple of videos at the Thunderbolts YouTube channel about this. Well, mostly they were centered around the electric comet idea, you know, how they, if this was indeed an interstellar object that entered the solar system from somewhere beyond, let's say, it should have, you know, shown the cometary activity of its own, but somehow it did not. And that was a problem. But again, if we're looking at the response from the sun at the same time, then maybe I've had this hypothesis that maybe well, in sort of an abstract terms, maybe the electromagnetic energy somehow distributed itself in such a way that the sun became active rather than this object, you know. So, but again, I can definitely say that not all the sun-grazing comets cause solar activity, but maybe there is some sort of energy distribution that causes, you know, some comets to flare up, and some comets do not flare up as they were supposed to, so to speak, but rather the sun flares up instead of these comets, you know.
I think that that type of
another interesting thing about this Oumuamua object is just that I'm currently working on another video for Thunderbolts about it, because there were lots of publications recently discussing how it might be, you know, aliens, because why not, and stuff. But I don't think it is, but anyway. So, but there is a definite observation that its trajectory is not the one that we would expect it to be. It's currently diverted from the initial predictions for about 50,000 kilometers or something like that, which is not much given the actual distance that it traversed.
Right.
But it's still significant in terms of, you know, the precision that we have in our orbital mechanics.
Well, yeah, because we're only supposed to have inertia and gravity, right? So.
Yeah, so I'm thinking currently that maybe it is related to this overall problem with Newtonian gravitation that we have. For example, again,
like
I'm
the
referring
pioneer
to
anomaly type thing?
Yes, exactly. I wanted to mention it right away. So maybe it's something like that, when we have such extreme, you know, trajectories, such extreme distances from the sun gained very rapidly. Maybe something is wrong just with our, you know, basic understanding of orbital mechanics, or maybe there is some other electromagnetic influence that we are currently not accounting for, so it could have caused something like that also. But it's at this point we just don't know, you know. It's open to interpretation. With for example, with Pioneer anomaly, as far as I understand, the scientific community kind of settled with the point that it was an anisotropic emission of heat. So basically, one of the sides of the spacecraft was much hotter than the other one because of this, you know, radioisotope thermal generators or whatever. So it was this emitted heat kind of propelled it a little bit, and over time it, you know, accumulated into some noticeable discrepancies. But maybe something like that actually happened with this Oumuamua thing, because even its rotational state is very peculiar. It's not just rotating around one axis, it's actually kind of tumbling. I've read many papers about that recently, so
Well, that's good, because if it was actually traveling in a straight line, I would say it's a spaceship.
I know. Well, I was wondering if the shape of it, how much because of its elongated shape, how much that affects its trajectory or the changes of how it behaves.
I'll tell you what. The first thing I thought about when this thing was coming in was, great, we're going to have to go save some whales.
Fine.
Star Trek 4?
Star Trek reference. But anyway, I wanted to note that even the elongated shape is only a hypothesis, if you like. It's an assumption, because
I've been getting Mr. Hanky out of it. So.
What we're actually observing is changes in brightness, and the rotation is inferred from these changes in brightness. So we don't even know whether it does look like that,
Well, the name comes from the Hawaiian Oumuamua, and this is the definition, meaning scout, and reflects the way this object is like a scout or messenger sent from the distant past to reach out to humanity. That's what it is.
Yes,
that's what happened.
The name comes from the fact. The name comes from the fact that the observatory that discovered the object is in Hawaii, so they kind of made an homage, I believe, or something like that. Yeah. But the name itself comes from the realization that this is probably an interstellar object, that it does not belong to the solar system initially, so it comes from somewhere out there. So it's a scout.
We're seeing it. I mean, we were talking about conic sections last week a little bit. Would you support by definitive statement that it's certainly a hyperbolic situation?
Yes. Its velocity is too high to be bound to the system, at least in the gravitational paradigm.
Mm-hmm.
I mean, its velocity is just too high for the sun to keep it around.
Right.
Just came in the system too quickly to be left there.
Mm-hmm. It certainly bent the shot.
See, that does lead to another explanation, though. If you assume, I'm not saying this is right, but if you assume that planets are somehow in a minimum energy configuration orbits where they're settled into these, following long magnetic field lines, that wouldn't be the case for something, coming in from the outside. So in other words, where magnetic forces don't seem to play a role in planetary orbits, they might have an effect on. Obviously, you wouldn't expect that to be in a minimum energy configuration already. So that might be where magnetism would play a role then.
Yeah, I would say it's a possibility. But Jim, can you kind of state in general, what do you think about the comets? I mean, in your theory, as I understand it, they would be constantly subject to this radial electric field. So what would that lead to, in your opinion? Jim? Huh? Yeah.
Yeah. Well, that was the idea. Remember, is that most things do follow pretty closely this, the gravitational orbits, and the idea of that is that they'd be pretty much shielded, so you wouldn't have to worry about obviously, there's no room for like electrostatic repulsion between planets and stuff. They can't be doing that, which is my argument for them not being, in fact, connected to each other that way. But they would still, that doesn't eliminate magnetic forces. I mean, if something is shielded and traveling through a magnetic field, that doesn't mean, that it's immune to that. Even if it's I I would suspect that short period comets would be most likely to be in like a minimum energy configuration, but not necessarily a long period comet, or for sure a comet in an open orbit you wouldn't expect to be in a minimum energy configuration in our system anyhow.
But maybe they've kind of, although they have these elliptical orbits that kind of traverse the different layers of this super Birkeland current that Don Scott is talking about, although they have all of that, maybe they've traverse these layers in such a way that it kind of does not change their orbits. So maybe it's like some sort of resonant type of orbit, So like one layer kind of compensates for another, or something like that. You know what I mean?
Right. Yeah, I was considering the effects of that too. Like, if that's one nice thing actually is, if there really were these shells of charge out there, that should do what you say is wash out over. We'd have to have really accurate measurements over short as they cross between shells. You might see an acceleration, a deceleration, acceleration, deceleration, but depending on the spacing of those shells, that could almost totally wash out in the observations too. So